Lighthouse Scientific Education presents a lecture in the mole series. The topic, percent composition. Material in this lecture relies on an understanding of the previous lectures, atomic mass and molecular weight, and math for chemistry, part 2, specifically the section on percent. The lecture begins with a definition of percent composition. A brief review of percent is provided, then a discussion on a set of rules for solving percent composition problems. The rules are then applied with 4 practice problems that cover different aspects of finding percent composition. Percent composition is defined as the mass percentage of each type of element in a compound. Basically, it is found by dividing the mass of an element in the compound by the total mass of the compound and converting that ratio into percent by multiplying it by 100. A useful check is that the sum of the percent compositions of all of the elements in a compound must equal 100. The sum of the parts must equal the whole. To get some perspective, consider a molecule of water, H2O. Water's molecular weight is 18.02 grams per mole when rounded to the 100th place. In finding the percent composition of the oxygen in water, the mass of the compound in the percent equation will be the water's molecular weight of 18.02 grams. Since that is the mass of a mole of water, the value for the mass of the element, the numerator, will be the atomic molar mass of oxygen, which the periodic table shows to be 16.00 grams per mole. Substitute that mass of 16 grams in for the mass of the element. Percent doesn't have units, so the unit grams should cancel out, and they do. The solution to the percent composition of oxygen is found by dividing 16.00 by 18.02 and multiplying that value by 100. It is 88.80%. 88.80% of the mass of a water molecule comes from the oxygen. We could repeat the process and substitute 2 hydrogens' atomic molar mass for the mass of the element and get the percent composition of hydrogen. Or, seeing that there are only 2 elements in water, and we calculated the percent composition of one of them, we can deduce the percent composition of the other. Earlier, it was remarked that in a compound, the sum of the percent composition of all of the elements equals 100. Mathematically, that is expressed as 100% equals the percent composition of oxygen plus the percent composition of the hydrogens. Inputting the 88.80% for oxygen leaves an equation with a single unknown percent hydrogen, which solves to 11.20 for the percent composition of hydrogen. That mathematical trick relies on the understanding of percent. So, before proceeding into the step-by-step rules for getting percent composition, a brief overview of percent will be presented. Students who feel comfortable with percent should skip the review and go into the rules. Percent is simply a ratio or fraction taken 100 times. The word percent means per 100. The purpose of percent is to present a ratio or fraction value as a larger number, one people feel more comfortable with. It has no other role. In mathematical terms, it is a ratio or fraction, numerator over denominator, times 100. Written in this form, we see the value of the ratio is converted into a larger number by multiplying it by 100. Adding some context to the terms numerator and denominator, we see that the denominator represents the size of a whole thing, or how many parts make a whole. In percent composition, it is the whole mass of the compound. The numerator represents the portion or part of the whole. In percent composition, it is the mass contribution of a single element. More commonly, the percent equation is presented with the numerator as the part and denominator as the whole. When solving percent problems, a second form is often used. Part over whole equals percent over 100. This form allows cross-multiplying, which makes the solving of percent problems much easier. For a more detailed explanation of percent, see the Math for Chemistry Part 2 lecture. On to rules for determining percent composition. A distinction needs to be made here because there are two forms that percent composition problems come in. The first type gives the percent of each element in a compound and asks for a determination of the empirical formula. These types of problems are covered in the empirical formula lecture. Percent composition and empirical formula are generally taught together. It is helpful to pair these lectures. The second type has us given compound information and asks for the mass percent of each element. These are the types of problems covered in this lecture. To further break down these problems, there will be ones that just give a chemical formula, and those that give no formula but do give masses for the elements of a compound. A set of rules is offered that solves both types of percent composition problems. As these problems are often in the form of word problems, the general process of solving word problems should also be followed. That is, take time with the problem. Search the problem for the known and unknown values. Write them down. Then identify a relationship or set of relationships between known and unknown values. When the relationship is found to be getting percent composition, then apply these rules, starting with getting the mass of the compound. This will be the denominator of the percent fraction. The mass will either be found by calculating the formula weight of the compound, if the formula is given. Remember, formula weight is a broad term that encompasses the molar mass or molecular weight of a covalent compound and the formula unit weight of an ionic compound. Another way that the mass of a compound is found is by adding the masses of the elements given in the problem. This applies when no formula is given, but mass data is. Adding all of the given masses will be the mass of the compound used in the denominator of the percent equation. It is not a formula weight, but that's okay because the masses of the element are not atomic molar masses. These masses are generally values determined in experiment in the lab. Step 2. Set up the percent equation or equations, depending on how many elements are being solved for, with the element's mass contribution in the numerator and the compound mass in the denominator. There should be full canceling of units. Finally, step 3, multiply the ratio by 100 to get percent. While percent composition problems look very busy, they are straightforward to solve. We will solve 4 of them using these step-by-step rules. The first example. An experiment on an unknown is found to contain 3.461 grams of carbon, 0.615 grams of hydrogen, and 1.635 grams of oxygen. What are the percent composition of the elements? Being a word problem, we will take some time and review the problem before trying to solve it. Specifically, what are the known and unknowns in this problem? Given are 3.461 grams of carbon, 0.615 grams of hydrogen, and 1.635 grams of oxygen. What is not known are the percent composition of these elements. From this setup, we identify the problem as one using the percent composition rules. This conclusion may seem a bit obvious, but the practice of evaluating the problem before solving it will generally serve the student. The first step is to get the mass of the compound. Can it be done by calculating the formula weight of the compound? Well, the actual formula of the compound is not given. The problem claims that the compound is an unknown and only gives mass values of its constituent elements. The compound mass is therefore gotten by adding the masses of the elements. Will this produce a formula or molecular weight? No, it will not. If the experiment was performed with twice as much of the unknown compound, then each of the element masses would be doubled. The element's contribution to the compound mass is in relative proportion. So it doesn't matter if the compound mass is determined by adding weights, like this problem, or by calculating a formula weight. Both ways have the same proportion of compound mass to element masses. The ratio is the same. Okay, getting back to the compound mass. To restate the definition, the mass of the compound equals the sum of the masses of the elements. That is 3.461 grams of carbon, plus 0.615 grams of hydrogen, plus 1.635 grams of oxygen. The calculator gives the mass of 5.711 grams for the entire compound. We will keep those values handy. There are 3 elements, and the percent composition for each has to be determined individually, starting with carbon. Since we have the mass of a compound, it is time to move into step 2. Set up a percent equation. That begins with the ratio of mass of the element to mass of the compound. The mass of the element carbon is 3.461 grams. The mass of a compound was just calculated, and it is 5.711 grams. The math can be done here or at the end of the problem. We will do it here. The first thing to note is that the units of grams cancel out. That is important because the final answer, percent, does not have units. 3.461 divided by 5.711 is the decimal 0.606. The last step is to multiply by 100 to get percent. 0.606 times 100 equals 60.6%. The unknown compound is composed of 60.6% carbon. We'll keep track of that value. 1 down. What about hydrogen? What is its percent composition? For that, we return to the setup equation. This time, the mass of the element is the mass of hydrogen, 0.615 grams. The compound mass is still the 5.711 grams. Canceling units and dividing 0.615 by 5.711 yields 0.108. To get percent, multiply the value by 100. Hydrogen's percent composition is 10.8%. Add that value to the panel with carbon. We will return to these percents after getting the percent composition of all 3 elements. We only have oxygen to deal with. Like with hydrogen, solving the percent composition has us returning to the percent equation. This time, the element mass belongs to oxygen with a value of 1.635 grams. The mass of a compound is unchanged at 5.711 grams. Canceling units and dividing 1.635 by 5.711 yields the decimal 0.286, which is converted into percent by multiplying it by 100. The percent composition of oxygen in the compound is 28.6%. Add that to the panel, and the question is solved. Are we done? The short answer is yes. The long answer is no. We should double check our results. How do we do that? By recognizing that the whole is the sum of the parts. That is, the sum of the percent from each element must equal 100. The addition of these 3% values should be 100, or something that rounds to 100. Again, these are experimental values and will have some error, so exactly 100% is not always obtainable. In this case, 60.6 plus 10.8 plus 28.6 does give 100%. That should give us confidence in our results. Okay, let's have another problem. What are the percent composition of the elements in Epsom salt? Epsom salt usually comes as a hydrate, that is, it has attached waters. Example 4 also has a hydrate for a compound. In that example, we will consider the attached waters. Here, we will not. Word problems should be met with patience and carefully considered. We should ask, what are the knowns and unknowns? The chemical formula of magnesium sulfate is given, and the unknowns are the percent composition of the elements in the formula MgSO4. What is the relationship between the known and unknown values? It is the process for determining percent composition, which begins by getting the mass of the compound. There are two options for getting the compound mass: calculating the formula weight or adding the masses of the elements. Which one should we use in this problem? Well, there are no given masses, so the choice clearly falls to calculating the formula weight for the compound formula. At this point in their studies, the student should feel reasonably comfortable getting formula weights. Still, it can't hurt to run through the process again. In 1 mole of MgSO4, there is 1 mole of magnesium, 1 mole of sulfur, and 4 moles of oxygen. The 1 to 1 to 4 comes straight from the subscripts of the elements in the compound, with an absence of subscript implying a 1. A second point needs to be made considering the MgSO4. It is an ionic compound with a polyatomic anion. If we were completely correct, the magnesium would not be 1 mole of magnesium, but rather 1 mole of the magnesium ion Mg plus 2. While this doesn't change the formula weight, it does keep us on our toes. To get a formula weight of the compound, we need to convert the moles of these particles into grams. The conversion factor for moles to grams of an element is the atomic molar mass. The actual masses will be gotten momentarily. As written, the unit moles will cancel out, leaving the unit grams. To get the actual masses, we will consult a periodic table. We find the atomic molar mass of magnesium to be 24.31 grams. Sulfur has an atomic molar mass of 32.07 grams, and the atomic molar mass of oxygen is 16.00 grams. Returning to the formula weight calculation and inserting 24.31 grams for magnesium ion, 32.07 grams for sulfur, and 16.00 grams for oxygen, we are ready to get the masses. For the magnesium ion, cancel out units, and doing the math gives 24.31 grams of magnesium ion. For sulfur, cancel moles and do the math for 32.07 grams of sulfur. And finally, 4 times 16, 64.00 grams of oxygen. All that is left is to add up the masses of the elements. 24.31 plus 32.07 plus 64.00 is 120.38. In 1 mole of magnesium sulfate, there is 120.38 grams of magnesium sulfate. We need these values as we proceed in determining percent composition of the 3 elements. Starting with the magnesium ion. Since step 1 is complete, move to step 2 and write out the percent equation. For the mass of the element, insert the 24.31 grams of the magnesium ion. For the mass of the compound, insert the 120.38 gram formula weight of magnesium sulfate. The unit grams will cancel out, and dividing 24.31 by 120.38 gives a value of 0.202. Step 3 is turning that decimal value into a percent by multiplying it by 100. 0.202 times 100 is 20.2%. 20.2% of the mass of magnesium sulfate is magnesium ion. We'll keep track of that value for the final double check. Magnesium is done. How about the sulfur? That requires us to return to step 2. This time, the mass of the element is 32.07 grams of sulfur. The compound mass is still the formula weight of 120.38 grams. Gram units cancel, and the math of 32.07 divided by 120.38 is a value of 0.266. This value is converted into percent by multiplying it by 100. That is 26.6%. 26.6% of magnesium sulfate is sulfur. We'll keep track of that value too. That just leaves the oxygen. And again, we will return to step 2 and insert 64.00 grams of oxygen into the mass of the element and that same 120.38 grams of magnesium sulfate for the mass of the compound. The division yields a value of 0.532. The last step is to convert that value into percent by multiplying it by 100. This will yield a final value of 53.2%. Oxygen comprises 53.2% of the mass of magnesium sulfate. And the problem is solved. As a double check, we note that the sum of the percent composition of the elements must equal 100%. Therefore, the value of 20.2 added to 26.6 and 53.2 should give a sum of 100%. All the mass of magnesium sulfate has been accounted for. The third example is a word problem with an extra dimension. When heated, calcium metal can react with the oxygen in the air to produce a metal oxide. 5.00 grams of calcium is heated and forms 7.70 grams of calcium oxide. What are the percent composition of the elements calcium and oxygen? This problem seems similar to the problem in the first example. It is, however, a bit more complicated, and it will show why it is always a good idea to consider the problem before pursuing the answer. What are the known and unknowns in this problem? The starting quantity of 5.0 grams of calcium is given, as is the mass of the final product, calcium oxide. The 7.70 grams is the mass of the compound and will be the denominator in the percent equation. What is unknown, aside from the percent composition, is the mass of the oxygen that combines with calcium to form calcium oxide. The mass is not given, but the question specifically asks for the percent composition of oxygen. Add oxygen as an unknown. We've seen a couple examples of percent composition so far, and in each case, the mass of the element was either given or its atomic molar mass was used. As we are not using formula weight for the compound mass, the atomic molar mass is not an appropriate mass for the element. We need another way of getting the mass of oxygen. We need a relationship between what we know and what we don't know. In this case, we can use a relationship that says the whole is the sum of its parts. Put into a mathematical form, it says that the mass of the whole of the compound, 7.70 grams, is equal to the mass of its parts, which are the 5.00 grams of calcium and the unknown amount of oxygen. When shown in this perspective, the amount of 2.70 grams for oxygen's contribution becomes evident, or at least can be calculated. Add that value to the setup, and we're ready to move on to the rest of the problem. Find the percent composition of the calcium and oxygen. That begins with step 1. Get the mass of the compound. A look at the information we have already gathered shows that the mass of the calcium oxide was given in the problem. There will be no need to calculate the formula weight or add the masses. With that in hand, get the percent composition of the calcium. Step 2 is to write out the percent equation that has the mass of element over mass of compound and substitute in the 5.0 grams of calcium for the element mass and 7.70 grams of calcium oxide for the mass of a compound. Note the grams cancel out, and doing the math, 5.00 divided by 7.70 is 0.649. To get percent composition, multiply 0.649 by 100 for a final value of 64.9%. 64.9% of the mass of calcium oxide is due to the calcium. As for the oxygen, return to step 2 and insert into mass of element 2.70 grams of oxygen, and into mass of compound 7.70 grams of calcium oxide. That math produces a value of 0.351, which we can convert into percent by multiplying it by 100. The final value is 35.1%. 35.1% of the mass of calcium oxide is contributed by the oxygen. That should complete the problem. However, we're going to look at a shortcut in solving for percent composition of oxygen. It involves the expression that the sum of the elements percent must equal 100, which is what we find if we look at 64.9 plus 35.1. It does give 100%. Consider for a moment that we never calculated the 2.70 grams of oxygen. Therefore, we were unable to come up with a 35.1% oxygen. We can still get that percent in a manner very similar to how we came up with the 2.70 grams. It follows from the equation that says the sum of the parts is equal to 100. We calculated the percent due to the calcium as 64.9. The part due to the oxygen is, we'll say, unknown. We have another example of an equation with a single unknown. A bit of math has oxygen needing to be 35.1%. That is, to sum to 100. Same basic concepts as when we calculated its mass. A lot of time and effort can be saved in recognizing an unknown value can be solved if it can be put into an equation where it is the only unknown. The last practice problem involves a hydrate. What is the percent composition of water in the hydrate BaCl2 with 2 waters? Barium chloride is considered a hydrate because it is a compound that includes water molecules. They are physically attached. Usually it is a very specific number of water molecules. Here it is 2 waters, and the dot between the barium chloride and the water is what signifies that it is a hydrate. For Epsom salt, the dot says there are 7 attached water molecules. For both of these compounds, those waters can be driven off with heat, but given the opportunity, the compound will attach water molecules. The question should be reviewed for what is known and not known. The molecular formula of the compound is known, and the percent composition of water is unknown. Note that the question asked for the percent composition of a molecule, water. The previous examples have asked for the percent composition of elements. The difference, however, is only one of terminology. The water in this problem is the part of the whole compound, just as the element is a part of the whole compound. As such, this problem can be solved in the same manner. Solving the problem requires an application of the steps for finding percent composition. Moving into the first step, getting the mass of the compound, and we consider our options. Is the mass found by calculating the formula weight, or by adding the masses of the individual elements? By being given the compound formula and not any masses, the choice is made for us. There are several ways to approach getting the mass of a hydrate. Presented here will be calculating the mass of the individual compounds, the mass of the barium chloride, and the mass of the 2 waters. These masses will then be combined into the mass of the hydrate. The main reason for taking this tact is that we're going to need the mass of the waters themselves in the percent equation. A secondary reason is that we want to start to build a collection of common molecular weights that come up so often that a recalculation is not always in order. Water fits that description. Starting with BaCl2. An interesting question here is to ask whether this compound is ionic or covalent. Well, it contains an element from the left-hand side of the periodic table and an element from the right-hand side of the periodic table. That's a good indication that BaCl2 is an ionic compound. From the formula, it can be seen that 1 mole of BaCl2 contains 1 mole of barium ion and 2 moles of the chloride ion. These mole values need to be converted into gram values using the conversion factor of atomic molar mass. Remember, that we can use the element's atomic molar mass for the ion's atomic molar mass. Referring to the periodic table, barium is found to have an atomic molar mass of 137.33 grams per mole, and chlorine, a value of 35.45 grams per mole. Insert in as a conversion factor 137.33 grams per mole for barium ion and 35.45 grams per mole for chloride. The mass of barium is solved by canceling units and multiplying to get 137.33 grams of barium ion. The moles of chloride cancel, and 2 times 35.45 gives a mass of 70.90 grams for chloride. Summing the masses of these ions gives a formula weight of 208.23 grams for barium chloride. That takes care of the barium chloride. Now to the water. And there are 2 common approaches for getting water's mass contribution. Both begin with the recognition that for every 1 mole of barium chloride hydrate, there are 2 moles of H2O, which can be written as 2 times 1 mole of H2O. The first approach is to treat water like a molecule and get its mass by getting the masses of the elements that make up the water. And in 1 mole of H2O, there are 2 moles of hydrogen and 1 mole of oxygen. Therefore, in 2 moles of H2O, there are 4 moles of hydrogen and 2 moles of oxygen. We can take these values, along with the atomic molar masses of the hydrogen and oxygen, and calculate the mass contribution of the waters. Or, we can start to build a library of common molecular weights and simplify the problem of calculating the grams of 2 moles of H2O by multiplying the 2 moles by the molecular weight of H2O. Early in the lecture, we calculated that as 18.02 grams per mole. The molecular weight of water comes up frequently in the study of chemistry, and it's worth memorizing its value. The math gives a gram value of 36.04 grams. Quite a bit easier. Both approaches work. One is easier. That is the mass contribution of the 2 compounds. Now we need to find the mass of the whole compound, the whole hydrate, the barium chloride with the waters. That is the sum of the compound masses, 208.33 for barium chloride plus 36.04 grams of water. That gives 244.27 grams for the barium chloride hydrate. It's time to calculate the percent composition of water in the compound. Step 2 calls up the percent equation. A slight modification in terminology is needed here because the problem asks for percent composition of water and not of an element. Changing the numerator mass elements to mass parts broadens the equation and allows for the mass of water, 36.04 grams, to be added in the numerator. The denominator mass is the hydrate, 244.27 grams. Grams unit cancel out, and the math of 36.04 divided by 244.27 gives a value of 0.148. The last step is to convert it into percent by multiplying by 100, producing a percent of 14.8. 14.8% of the barium chloride hydrate is water. And that is the last of our examples. Recapping the lecture, in a review of percent, we saw that percent is a ratio taken 100 times. Percent composition is the mass percentage of each type of element in a compound. It can be expanded to include any part of the compound, such as the water in the hydrate. It is found by dividing the mass of an element or part by the total mass of the compound and converting it into percent. Importantly, the sum of all elements percent must be 100. To find percent composition of an element or part, first get the mass of the compound. Generally, that involves 1 or 2 procedures. Calculate the formula weight if the formula is given, or add the masses of the elements if they are given. From there, set up the percent equation or equations with elements mass contribution in the numerator and compound mass in the denominator. Finally, multiply the ratio by 100. A double check can be done by adding all of the element's percent compositions together. It should sum to 100. And that concludes our lecture. Be sure to follow this lecture up with a look at the empirical formula lecture. That also contains percent composition problems. These two lectures are usually studied in tandem.